think we're good to go. My name is Raveen Kumar, and I want to welcome Ben Cohen. He's going to be doing time interrupted, measuring intervention effects with interrupted time series analysis. I just want to remind everyone, shut your cell phones off, try and turn the volume down on your laptop so we don't have any interruptions. All the talks and tutorials will be recorded, so they'll be online. PyData records all of them, so you can watch the other recorded PyData talks from New York or Cordoba as well online if you enjoy this format. And can you all help me give a warm welcome to Ben Cohen? All right. Thank you.
Hi everyone, and welcome. Sorry for the AV difficulties, but first talk of the day. So there you go. So this talk is time interrupted, measuring intervention effects with interrupted time series analysis. A little bit about myself. My name is Ben Cohen, and I'm a data scientist at Warby Parker. Sorry, the clicker. Oh, there we go. Sorry, I'm a data scientist at Warby Parker. For those of you who aren't familiar, may not be familiar with Warby Parker, this is a bit of our mission statement from our website, but essentially we're a company that sells eyeglasses and sunglasses. We were founded about 8 years ago, and we started out as an e-commerce company. But we've now expanded a lot, and we also now have around 80 retail stores in the United States and 2 in Canada. And a big part of our business model is that we do a lot of things in-house, everything from designing our glasses to running our own customer service, and that extends to our tech infrastructure as well. So while we do use some off-the-shelf software, we've also written internal software for a lot of things in our business, everything from supply chain management to order processing, CRM, our retail point of sale. And what this means is that we have a lot of data. So this data science team at Warby Parker really supports stakeholders throughout the company by helping them make better decisions with data. And like I said, we have a lot of different kinds of data that we work with. But this talk is about some work that we did with the marketing team. So what is interrupted time series analysis? It's a form of causal inference, and it's designed for situations where traditional experiments are impossible. And I'll give some examples of the situations in a bit, but first I want to go over what I mean when I say traditional experiments. So this comes up a lot in digital performance marketing. So this is an area where we often apply experimental design. And we have a lot of tools built around digital marketing to help us. And basically, the way that they work is they give us the ability, the revolutionary ability really, to do direct attribution in advertising, right? So when you look at an ad online, we know, who sees it, who clicks on it, what they do later on our website, whether they become a customer, et cetera. And a lot of our industry is built around this. One of the core tools that we use here is A/B testing. And this is something that's enabled by this direct attribution. So let's talk about A/B testing. I'm sure that a lot of people here are familiar with it, but I'm just going to give a brief overview. The idea is that we have some population of customers or of individuals, and we randomly bucket them into two or more groups, and those groups, could be called treatment and control. And we show them different versions of something, so different versions of our website or of an advertisement. And then for each of those groups, we measure target metrics like conversion rate or clicks on the website, et cetera. And then we can compare the metrics for those two groups, and we can use a statistical model to make some inference about the effect of the differences between what we showed them. And so this could be a traditional, kind of null hypothesis significance test, or a Bayesian model. There's lots of different approaches to A/B testing, but that's the basic idea. So now the problem that happened recently is that we wanted to do a national TV campaign, and we haven't done this a lot. And our marketing team came to us to ask for help in figuring out how to measure the impact of this. So, we're showing national TV ads. Did we make money from this? And so there's a big problem with this, which is that with TV, there's no way to randomize exposures. And beyond that, there's actually even no way to even know who saw the ad. So a lot of times, you may have aggregate numbers about how many people watched a certain TV program. But when you're talking about an individual person coming to your website, there's no way of knowing whether or not they were exposed to a TV commercial. So one thing that you could do to sort of replicate the idea behind an A/B test is geo-targeting, right? So you could run the ad in certain cities or certain markets that are similar to each other and compare across geographies. And that way you could sort of capture some of the idea behind an A/B test, although it wouldn't be strictly randomized. But this has one big drawback, which is that it's really expensive. It turns out that it's way more expensive on a per impression basis to do locally targeted TV ads than to do national ones. And in our case, we really wanted to run ads nationally in order to get that larger reach. So we needed a different approach. So I want to take a step back and ask a fundamental question. How can we know if something we did had an effect? So the big problem is that there are a lot of different causal factors that can impact how many people go to a website or buy a product, right? So it could be that the ad that we showed them was the causal factor, but it could be something about who they are, their demographics. It could be other ads that they saw, or all kinds of different things, the time of day. And so you want to control for the ones that you care about, in this case, exposure to the TV ad, and control for all the other ones that you don't care about. And so, in science, we have a gold standard for this. It's randomized controlled trials. And this is, the classic experimental design behind, for example, clinical drug trials, right? The idea is that you randomly assign from your target population into treatment and control groups. And the idea behind this is that the randomization controls for your confounding factors, because if you start with the same group of people and you randomize them, then you can be pretty sure that the only difference between the groups is your treatment. And if this sounds familiar, it's because A/B testing is precisely a randomized controlled trial, but typically in a digital medium. And again, the problem here is that with our TV example is that we can't have a control group because we don't actually control the assignment process, and we don't know who's in what group. We aren't able to observe people who weren't exposed to the intervention, right? We know that some people saw the intervention and some people saw the ad, and some people didn't, but we don't know which ones are which, right? And so stating the problem this way can lead to a useful reformulation of the problem, a restatement of the problem, which is what would have happened if we hadn't shown the ad to anybody? So again, we know that out of the population, some fraction of people saw the ad, but we don't know who that is. But we can ask the question, what if we just hadn't done this at all and hadn't shown the ad to anybody? And this is an example of a counterfactual. And I put the definition up here, but basically a counterfactual is a scenario that didn't happen, right? And the idea here is that if we can guess the counterfactual, we can estimate the effect by comparing it with what actually did happen. And so this problem of guessing the counterfactual transforms the problem into a prediction problem, predicting the counterfactual. And fortunately for us, as data scientists, prediction is something that's our bread and butter. So this brings us to interrupted time series. So there are many ways of constructing counterfactual models, and there's a whole field of causal inference that deals with this. But I'm going to discuss one particular technique, and it relies on two important properties that this scenario has, and also lots of other similar scenarios. So this model, ITS, is a counterfactual model that works when, first of all, the intervention begins at a specific known point in time. So we know exactly what day and what time we started showing TV ads, right? And we control that. And then also we have sequential observations from both before and during the intervention. In other words, we have time series data about whatever metrics we care about going back into the past from before we were showing TV ads. And we also will continue collecting them sequentially afterwards. So to capture the idea here, take a look at this plot from a hypothetical campaign. So what we have here is a time series. This could be sales or some other metric that you care about. And the dashed line indicates where in time the campaign starts. And so just looking at this plot, I'm sure everyone here would intuitively conclude that, that this campaign had a positive effect. And what's going on here is that based on our understanding of the world and our beliefs, we have a strong prior that the data generating process would have continued in a similar way absent the intervention. So essentially what you're probably doing mentally is filling in the counterfactual like this. And it's precisely this intuition that the technique of ITS seeks to formalize. This goes by various names. Sometimes the counterfactual is referred to as a baseline prediction. I like the term interrupted time series because it highlights that what we're looking for is a discontinuity in the time series. And in fact, ITS could be considered a special case of another causal inference technique or suite of techniques called regression discontinuity. And it's a special case because here the discontinuity happens in time. And this technique is frequently used in econometrics and social science. And it has a lot of other potential applications, particularly in public health, right? So if you do some sort of population level policy change or in education, other public policy. Another potential application is an outage postmortem. So like let's say your website goes down and you want to assess what the impact was on your business, but you actually don't have any data from when that happened. Another one is when you have to make a website changes, but you can't A/B test, right? So sometimes there may be, depending on your industry, there may be a regulatory reason or some other higher corporate policy reason why you have to make some change to your website or to some product, and you're not allowed to A/B test it, right? Another potential application is if you have some press piece about your company or some PR event, something out of the ordinary, and you want to measure the impact. So I'm going to go on and continue using this TV campaign as a motivating example, but I just wanted to highlight that it's a very general technique. It has a lot of potential applications. So how do you go about building a time series counterfactual? So let's look again at this simple example. And when I say it's simple, I deliberately made it as simple as I could. So our data here is just drawn from a normal distribution. So it's just white noise with a mean that changes once. The mean jumps up when the intervention happens. And so our counterfactual in this case is just that the mean would have stayed the same. So in a case like this, all you have to do is look at the summary statistics, look at a histogram of the data from before and after, right? And you just have two normal distributions, and so you can use your standard toolbox of statistical tests and models to calculate the lift. But of course, in the real world, we know that our data will seldom or never look like this. And in particular, it will tend to differ in two key respects, which I'll discuss in turn. So the first one is non-stationarity. And so in the previous example, both the mean and the variance of our time series stayed the same over time. But that's not necessarily going to be the case. So in this example, the mean is changing over time. And what we have is that the sales were actually already trending up even before the intervention. And what this means is that if we just naively summarize the data from before and after, like we did before, we're going to get a nonsensical and misleading result. And in particular, if you just naively average out the values here, you'll see that the variances of these two distributions look totally different, but that's not really capturing what's really going on. So even if you just fix the mean at its most recent value, you're still going to overestimate the lift significantly here because, again, you're not capturing the fact that that upward trend. And in fact, if you think about this as a business problem, overestimating the effect of your ad spend is actually the worst case scenario, because it means that you're going to be losing money and you won't know it. Right? You'll be wasting money on ads that don't work. So what you really want is a model that understands how the distribution is changing over time and how we can extrapolate that into the future. Right? And so this is where time series models come into play. And the other big problem is, other than non-stationarity, is autocorrelation, right? So you could have a mean that roughly stays the same over time, but the values actually sort of meander around the mean. And what's going on is that when you have autocorrelation, then the value at any particular time step is correlated with the value at a previous time step. So it's more likely that you'll see small changes locally as opposed to large changes. And you can diagnose this with an autocorrelation plot. And by the way, if you had a chance to go to there was an excellent time series models tutorial yesterday where we went over some of these things. But anyway, unfortunately, these two properties knock out many standard statistical models and tests and regression models because a lot of these techniques that we're used to using for A/B testing make an assumption, an IID assumption about the data, that it's independent and identically distributed. And unfortunately, what happens here is that autocorrelation violates the independence assumption, and non-stationarity violates the identically distributed constraint. So this is why we need a dedicated time series model to do this kind of prediction. And you may have heard of some of these different types of models. There's a lot of them out there, exponential smoothing, ARIMA, et cetera. If you look online at how many different time series forecasting packages there are literally hundreds, maybe thousands of them. So I'm not going to go into all of them, but I do want to talk about what they sort of have in common, which is that fundamentally what they all try to do is to make predictions by explicitly modeling temporal structure in the data. So this time dependence in the data, you can think of it in one sense as a nuisance because it means that you have to throw a lot of the standard toolbox out the window. But another way of thinking about it is that it's actually really useful because this temporal structure, this time dependence, carries a lot of information about the underlying process and therefore predictive power. And this is what time series models try to take advantage of. So, like I said, I'm not going to talk about all the different ways that you could do time series modeling. You could really use any of them for this technique, but I want to talk about the types of features that can exist in real-world data and the types of things that your model might have to account for. And in doing so, I'll explain sort of how we decided on what tool to use. So starting off simply again, you can have random noise that may or may not have autocorrelation. You can have trend, and it may be nonlinear, right? So the slope of the trend can change at different points in time. You can have day of the week seasonality. This is very common for business data, right? Like people shop on certain days of the week, or people do different things at different times. And then on top of that, you can have a lower frequency periodic effect, of annual seasonality, where things happen at different times of the year. And you can have holiday effects where specific days of the year tend to be outliers because of something that, that happens on that day. I think in this example I used National Donut Day and National Bagel Day as the holidays in this simulated data. And the last thing, another thing is that you can have other covariates that have some sort of causal effect on the data. So in this example, there's another time series which is your spend across other marketing channels, right? So somebody might have seen some of your online ads, and that could affect how they behave, in addition to how they whether or not they saw a TV ad. So another thing that you really want from a model, especially in this context, is prediction intervals. it's very important in this particular application to have a way of quantifying uncertainty. Because again, the purpose, if you think about the purpose of doing this kind of modeling, this kind of attribution or lift modeling, is that it's really, in some sense, risk mitigation. You want to make sure that your spend has a positive return on investment, and you want to have a sense of how confident you are about that. And so if you only have a point estimate, it's very difficult to know how much to trust that. For example, if our model says that our ad generated a 5% lift, it's really different from a business perspective if that confidence interval is between 2 and 7%, or if it's between -5 and positive 15%, right? That matters a lot in terms of how you decide how to allocate resources as a business. So for this type of problem, having reliable prediction intervals can be just as important, if not more important, than just the accuracy of the prediction itself. But there's actually a big problem with generating prediction intervals or uncertainty bars in time series forecasts. And it's summed up in this quote by Hindeman from his textbook on time series forecasting. But basically what it says is that typically time series models have very poor empirical coverage of their prediction intervals. And there are a number of reasons with that. I'll get to some of those later, but in large part, this happens for a technical reason, which is that a lot of traditional models like ARIMA will incorporate a random error term into the model, but they won't necessarily incorporate uncertainty in the parameter estimates. And actually, for all but the simplest time series models, there's no closed form or analytical way of incorporating that kind of uncertainty. And so there are really two primary options that people use. One is bootstrapping, where essentially you're resampling from your training data. And this actually is a little bit perilous for time series data because of that autocorrelation and non-stationarity, right? Like, how do you resample from a time series? It's actually pretty complicated. And then the other one is Bayesian inference, where you're actually fitting, instead of point estimates, you're fitting a posterior distribution for your parameters. So ultimately, we decided to go with a library called Prophet. It's a Facebook-released open source project, and it is a Bayesian. It uses a Bayesian inference engine under the hood. And one thing that's really cool about it is that it uses Stan, which is a Bayesian inference tool on the back end, but it has APIs in both R and Python that are basically 100% feature compatible, feature equivalent, et cetera. And it's built with daily and sub-daily business data in mind. It supports all these things I mentioned before, like changing trend, multiple different levels of seasonality, external regressors, all that stuff. So, I'm not being paid by Facebook to pitch this. We found it very useful, but your mileage may vary. But we found that was a good fit for this problem. So now I'm going to talk about how you actually go about training and prediction for interrupted time series model. So let's go back to our simulated data set that I was showing you before. So this is the same artificial data set, but I've added a simulated campaign period where I added about a 10% lift after the dashed line. And this actually illustrates that because of the complexity of the data here, it's very hard to eyeball this and actually know. So that's why we need a model. So recall that our counterfactual is that if we hadn't done anything, that the data generating process would have continued in essentially the same way. So what that means is that what we're going to do is use the historical data up until the beginning of the campaign as our training data. And then we're going to make a prediction for each time step during the campaign. But of course, as good data scientists, we also need to be able to test our model rather, and we want to do that on out-of-sample testing data. So this is another tricky thing to do, but we went with a simple approach where we cut the data off a little ways before where our predictions will start, and then use that as our test set. So we're going to train a model using all the data up to that point, and then measure the accuracy. So now you can check the accuracy of its predictions on the test set and measure your accuracy metrics. So just a word of warning here, you want to be careful about choosing accuracy metrics for a time series model because some traditional regression accuracy metrics like root mean squared error can have some problems where they're not scale invariant if the variance changes over time, right? So you just want to be careful about that. One popular choice is mean absolute percentage error, but there's other ones including information criteria and various other ways of measuring how good your model is. You also want to look at autocorrelation in the residuals or the errors of your model because if your errors are correlated in time, it basically means that you're leaving predictive power on the table. You're not accounting for all of the temporal structure, time-dependent structure of the data. And then lastly, you also really want to look at the empirical coverage of your prediction intervals. So basically, if your confidence interval says, if you have a 95% confidence interval, you want to check that it actually contains the true value roughly 95% of the time. And again, that's because of this, this problem with coverage of prediction intervals. And so, you kind of just want to calibrate your uncertainty metric so that you can trust it. So once you've done this and you're satisfied with your model and your hyperparameters, et cetera, you then can retrain the model using all of the data up to the beginning of the intervention and make your forecast. So here you can see that the blue line is the counterfactual prediction and the green line is the actual observed data. And it may be hard to see in this view, but it looks like the blue line is slightly below the green line, meaning our model thinks that there was some positive effect from the campaign. So let's talk about how we can actually analyze that lift and try to quantify it. So one really nice thing about using a Bayesian framework like Profit is that it gives you samples from the posterior predictive distribution. And the best way to think about this is that it's basically a probability distribution over possible futures, possible outcomes. And the nice thing about these samples is that they're really easy to work with to generate all kinds of summary statistics. And you can work with them sort of empirically. So for example, this is how we get prediction intervals. You can generate prediction intervals by looking at the quantiles of your posterior samples. And here we can generate them for both pointwise, so day by day, and cumulative metrics. And this is really useful because, as you can see in this case, on any given day, it looks like there's a small positive effect, but it actually may not be outside of your margin of error. But you actually get more power when you look cumulatively, and that's because intuitively a small lift on any particular day could easily be a fluke. But if you see that same small lift every day over a long period of time, it becomes less and less likely that it's a coincidence. And so what you can see in the cumulative view on the right is that pretty quickly, as you look at cumulatively, the two lines, the counterfactual diverges from the actual observed values, and they move outside of the margin of error. And another thing you can do is actually get intervals around the lift itself, and you can do this just by subtracting the posterior samples from the actuals. And so in these views, I'm showing lift as a percentage. And here you can see even more clearly how the cumulative uncertainty actually tends to shrink over time. And you can see that for many individual days, we're not 95% sure that there's a positive effect at all, but that the margin of error is quite a bit smaller when you look cumulatively. But it's still useful to look at multiple different timescales because in real life, your TV campaign, your intervention may not have this simple, step change effect that the example has, right? So you can have some combination of a change in level or a change in slope. There can be a delayed effect, or there can be, decay, et cetera. And so if you want to get some insights into this, it can be useful to look at multiple different timescales. And lastly, another useful feature of using a Bayesian package like Profit is that it makes it really easy to answer probability-based questions like what's the probability that the cumulative lift was greater than or equal to 5%, or some other cutoff point that's meaningful to the business. And this is a really useful way of communicating results to stakeholders. So in the last section of the talk, I'm going to talk about some threats to validity. So, I've gone through interrupted time series analysis and maybe painted a little bit of a rosy picture of it. And the truth is that it's a very useful technique. But as always, there are caveats. So, in the literature, this is often referred to as a quasi-experimental design. And that's really, just to emphasize that it's not as good as a real experiment. Your counterfactual is not the same as having a control group because it's something that you didn't actually observe. It's something you're making an inference about. And so you can only have some sort of probabilistic idea about it. And therefore, you can't make nearly as strong of a causal claim as you could with a randomized experiment. Excuse me. So the first threat to validity I want to talk about is that there's some change in the underlying process. Basically, the underlying data generating process changed during the forecast period in some fundamental way. So this model assumes that any lift you see during the campaign period is attributable to your intervention. But that might not be a valid assumption. Something could change globally. The economy could tank, or a competitor could release a product. Some unobserved thing could happen that changes the fundamental dynamics of the process, of the system. And so there are two ways that I want to talk about that you can sort of mitigate this. So one is that you can look both before and after the intervention period. So if you have a scheduled end to your intervention, then under this counterfactual assumption, you would expect that things would kind of go back to the way that they were before. And so if that doesn't happen, that's a warning sign that something changed, something else changed that you weren't accounting for. And secondly, you can look at other similar time series that you think follow a similar process but should be unaffected by your intervention. So for example, if you have access to market level data for your industry, then you would expect that the same underlying global factors would affect that. But if your model is predicting that your ad boosted your competitor's sales, then that's probably a sign that something else is going wrong, that something else is going on that your model doesn't know about. Sometimes these kinds of changes can be modeled explicitly as confounding variables. So in this case, the problem could simply be that there are causal factors, known causal factors that your model doesn't account for. So for example, somebody could, somebody else in the business could have, increased the spend on some other marketing channel and they didn't tell you about it or something like that. Or, there was bad weather and so, nobody came into your store. And oftentimes, so in both of those cases, there's now an identification problem in your model. But if you can think of those factors and you have data on them, then you can add them as covariates into your model. So in the example I gave earlier, we include our spend across different channels in the model, and therefore, we can control for that. Lastly, even if there isn't some causal factor you're not accounting for, obviously your model could still be misspecified. It failed to capture reality. So, there could be problems with the convergence of your model. It could be overly confident. It could be overfitting, et cetera. All of the typical types of issues that we deal with in every kind of modeling. All models are misspecified to some degree. So you can never escape this, but there are certain things you can do to build trust. So one is that you can compare several models. So one practical example of this is, in doing a TV campaign, we work with an outside agency partner, and they have their own team of data scientists that built their own in-house attribution model. And we can compare the answers from the two models that were developed independently and get a sense of whether they agree or disagree. And that can give us some insight into how much to trust either one. And then another, a similar approach is to assess multiple outcome variables. So, you can look at sales, or you can look at click-through rate, or you can look at, unique visitors. You could look in retail or online, right? These are all different outcomes that are correlated with each other, but not perfectly correlated. So hopefully by modeling all of them separately, you could see if one of them had a spurious result, or whether they all agree with each other. So I'm going to conclude with some folk wisdom. It's difficult to make predictions, especially about the future. This is not a silver bullet, and it's just one of many ways that you can, look at marketing data or any other kind of data to try to assess the performance of your marketing or whatever you're doing. And if you have the choice, it's always best to do a controlled experiment. That's always going to give you the most reliable causal inference. But there are many cases in the real world where that's not possible. And in those cases, using a counterfactual method like interrupted time series analysis can oftentimes be the next best thing. So thank you very much, and I will take questions.
Thank you. Hi. I was wondering whether you could speak more to the business application of this at Warby Parker, and in particular, what kind of metrics you look at for the time series, and how you define the after intervention period, since I imagine people buy glasses relatively infrequently and may not interact much with Warby Parker otherwise.
Yeah, that's a good question. So. We look at a bunch of different ones, like I said. Obviously, and that's a good point that different metrics can have different time lags. So the first metric that we'll see, the place where we'll see the effect the soonest is if somebody comes to our website, right? That will happen pretty shortly after you see the ad. Although sometimes you may have to see the ad several times, or you may think of it later, right? In terms of our business, one of the really cool, unique things about our company is our home try-on program, and that's a program we have where you can try on 5 free pairs at home with free shipping and return shipping, et cetera, and you can pick which one you like. And so we look at the number of people who sign up for a home try-on, and then we have lots of historical data about how long it takes for people to convert from a home try-on, et cetera. And then we also, like I said, we have now a large chain of retail stores as well, and so we can look at metrics from those to see if a campaign is impacting whether people go into the stores or not. Other questions?
Can you share an example of a situation where this worked well, like you had high confidence in your counterfactual, and were there any situations where you tried this where you just couldn't find a good counterfactual prediction?
Yeah, so I think that one I don't know if I can give a specific example, but one type of thing that could happen that could be confusing, right, is that if your actual metrics are below where you predicted the counterfactual, that can be confusing, right, because there's not a plausible causal mechanism that says that doing more advertising will cause people to shop less. So that is a pretty good indication that there's something you're missing, that there was something wrong with your prediction. And in terms of when it works well, I think that, again, when you have agreement between the different KPIs or between different independent models that were made using slightly different assumptions, the more you have agreement between different methods, I think the more trust you have in it.
I have a question about comparing different channels of advertisement and then figure out like which one was more effective. Do you do any of that? Like basically compare the value of different channels, network, or TV advertisement versus digital or something like that?
Yeah, so that's an interesting question. So one of the things that we're trying to do here again is like model the other channels, and then this is a pretty unique situation in that we've recently started doing TV ads, right? So you have this like clear demarcation in time of when something starts and stops. As far as comparing other channels, yeah, I mean, I think that that's like a whole other topic, but there's all kinds of regression-based approaches that you can use for that. One reason that can be tricky to do actually is that you can often have a lot of multicollinearity between different channels. So there's a lot it's a fraught topic, and there's a lot of issues with identification there.
Can you talk a little bit about the data preparation for being able to do an interrupted time series? You kind of have this clean segment of data leading up to your intervention, but I can imagine there are times where there are different ad campaigns running in sequence, and sometimes right after the other, that might influence your after effect, and also will affect your attempt to do this on the next campaign.
Yeah, totally. Like I said, this is pretty new to us as a company, so we haven't had to deal with too many of that kind of situation. But I mean, I think that ultimately there's no free lunch, right? Like being intentional about how you design this is still, even though it's not a randomized experiment, it's still an experiment in the sense that we're deciding to start doing ads at a certain time, And so I think having some intentionality and communicating across the business about how you plan to launch these things, how you plan to measure them, I think that's really key to getting a good outcome.
So my name is Ravi, and I have a question regarding the ramp-up period. So when in one of your slides, you said there is when the intervention starts, so you was laying down a time series, and then intervention starts, and then you have a different time series. But in most businesses, there is a ramp-up period because the website is not rolled out to all users or things like that. The product is not rolled out to all the stores. So how do you analytically determine what should be the correct ramp-up period before you start measuring the effect?
Yeah, so I mean, that's a good question. I think, if you have a slow ramp-up period, then this may not be the best design because, again, like if you have the option to compare subgroups, some of whom were exposed and some weren't, then you can use other types of experimental or quasi-experimental designs. So interrupted time series is really targeted at situations where you don't have the ability to control the rollout in that way.
We have time for one more.
Sure.
Hi, my name is Saurabh. You mentioned about the cases where we can't do A/B testing, right? And we do a counterfactual. So how do we actually assess our counterfactual is, correct? Or how do you forecast our counterfactual compared to the original time series that has happened after the intervention or an effect?
Yeah, so I think that's why it's really, again, it's vulnerable to the threat to the validity that you have to make a pretty strong assumption that the underlying dynamics of the system, of the business, et cetera, are going to be relatively stable during the window that you're interested in, right? And so then, given that assumption, you can use your a typical suite of model checking tools. So it is really important to test these models on some kind of out of sample, holdout set. And so, like I said, there's a whole, the same toolbox you can use in general for assessing how much to trust a model, I think is applicable here. But again, it is vulnerable in that you have to make that assumption about the underlying process staying the same. All right. Thank you, everyone. If there are more questions, find me afterwards, and I'm happy to talk to people in person. Thank you.